The last class, we talked about continuous time Fourier transform. We developed the Fourier transform analysis equation as this. Then we developed the Fourier transform synthesis equation as this. Basically, a non-periodic signal can be broken down as a linear combination of complex exponentials where x of omega is the amplitude of these complex exponentials, and x of omega, which is the complex amplitude of the exponentials, is given by this integration. If x of omega is the Fourier transform of x of t, then we said that x of omega is a complex number. The Fourier transform is a complex number. It has real parts and it has imaginary parts. This is the rectangular form. In polar form, it has a magnitude and a phase angle. This is the expression in polar form. We want to consider the properties of Fourier transform. The first property we'll consider is conjugate symmetry property. This property simply says that if x of omega is the Fourier transform, then x minus omega is equal to the conjugate of x of omega, and that's for real valued. So if x of t is real value, the Fourier transform is conjugate symmetric. Simply states that x of minus omega is equal to the complex conjugate. Because of this implication, it implies that the real part of the Fourier transform is even, the imaginary part is odd, and the magnitude of the Fourier transform is even, while the phase angle is odd. This example, we did it in the last class. We arrived at this Fourier transform. The magnitude, we arrived the magnitude as this, then this was the phase angle we arrived at. When we plotted it, this is the time function, this is the magnitude plot, and this is the phase plot. We can see that the magnitude plot is an even function, while the phase plot is an odd function. And since the question e to the minus at u of t is real, then we add, the magnitude is even, we had an even magnitude, and we had an odd phase. That's the first property of conjugate symmetry. The next property we'll be looking at is time and frequency scaling. This simply means that a linear expansion in the time is translates to a linear contraction in the Fourier transform domain. For instance, this example, we did it the last time. This was what we got as a Fourier transform. Then dividing the numerator and the denominator by a, we are going to arrive at this. And we know that from the time and frequency scaling, we know that a linear expansion in time. So you have a here, this is in the time domain, corresponds to a linear contraction. So we have 1 over a. So in the time domain, you had a in the time representation, but in the Fourier domain, you have 1 over a. This is the property of frequency and time scaling. It simply means that when you in the time axis, when there is a contraction or expansion, the inverse is the case in the frequency domain. You have the duality property. Duality property simply says that when you have the Fourier transform of a when you have the Fourier transform of a signal, then actually the Fourier transform you can calculate the Fourier transform of the Fourier transform of that signal you already have. That's calculating the Fourier transform of the Fourier transform of the signal you got is straightforward. And the duality property stems from the fact that this is the Fourier analysis equation, where this is the Fourier synthesis equation. You can see that when you compare these two together, we can see that they are almost the same thing. So you have, the only difference is that the first one, the first equation is in terms of omega. So you have omega here, you have omega here. But the second one is in terms of time. So you have t here, and you have t here, you have omega here, then you have omega here. So when you look at this closely, you have x of omega here, you have x of omega here, you have x of t here, you have x of t here. Then basically these two are just the same thing. It's just the minus. There's a minus here and there's no minus here. So when you look at it this way, these are the same thing. These are the same thing. It's just the 1 divided by 2 pi, and there's no 1 divided by 2 pi here. So it simply says that if x of omega is a Fourier transform of x of t, duality property says that if you have another signal in the form of x of omega given by capital letter X of t, then the Fourier transform is equal to this original signal you have, but multiplied by 2 pi. Then omega is at minus, t is at minus omega. So we are going to use an example. If you have the signal x of t, the Fourier transform is given by this square non-periodic wave. Then looking at this signal x of t, this signal and this signal, they are actually in the same form. The only difference is that you have omega here, then you have your t here. The Fourier transform of this signal is given by this. And if you look at this, they are the same thing. And if you look at this, they are also the same thing. So the duality property tells us that the Fourier transform of a signal, x of omega being the Fourier transform of this, you can get the Fourier transform of this now in the time axis just by scaling with 2 pi. Instead of t, we are replacing it with omega, because the Fourier transform of this in this form is equal to the original function. We're going to be doing an example towards the end to clarify this. Expressing this mathematically, so I'm going to do the Fourier transform of this non-periodic square wave. This is the non-periodic square wave. So it has a value of 1. 1 is supposed to be here at from minus omega to plus omega. It has a value of 1 from minus omega to plus omega. Then when we try to get the original signal, we try to get this signal, we're going to integrate with respect to omega. Integrating with respect to omega, we'll get this. Then applying the limits, we get this. Then collecting the 2j towards this side, we're going to arrive at this. Then we know that this equation is a sign. Then we replace it with a sign. Then when we do some rearrangement, we're going to get this. So it simply means that the inverse Fourier transform of this is given by this. Then we want to do the Fourier transform of this signal of this particular non-periodic square wave. We're going to, so this is our definition of the Fourier transform. So in place of a function x of t, we are going to replace it with the limit. That's from minus t1 to plus t1. That's why we have this integral here. So instead of integrating from minus infinity to plus infinity, integrate from minus t1 to plus t1. When we do the integration of this, we arrive at this. Then applying the limit, we arrive at this. Then doing some rearrangements, we arrive at this. And we want to get the sign term, so we bring the 2j here. And this is the sign. And doing some rearrangements, we get this. Therefore, the Fourier transform of this square wave is given by this, where 2 sine omega t1 divided by omega is given by this representation. So it simply means that the summary of the duality property is that when you have the Fourier transform of a signal, in fact, you have 2 Fourier transform, and it means that the Fourier transform of the Fourier transform of that signal you have is known already. That's if you have the Fourier transform of one signal because of the property of duality. We'll do an example again on that to further explain it. The Passover's relation simply says that the energy in a signal in the time domain is equal to the energy of the Fourier transform scaled by a factor of 1 divided by 2 pi. So this is for the non-periodic case. Then for the periodic case, where you have x tau of t, the energy is given by the summation of the Fourier series, the squared, the sum squared of the Fourier series coefficient. We'll talk about the time shifting property. The time shifting property says that if x of omega is the Fourier transform of x of t, then x of t shifted in time by t naught, the Fourier transform of x of t that is shifted in time by t naught is equal to e to the minus j omega t naught multiplied by the Fourier transform of x of t. We go to the differentiation property. Differentiation property says that the differential of, if the derivative of a signal x of t, the Fourier transform of the derivative of a signal x of t is simply equal to j omega multiplied by the Fourier transform of x of t, which is x of omega. The integration property simply says that the integral of a signal, the Fourier transform of the integral of a signal is the Fourier transform of the original signal divided by j omega. Then you have a constant because it's just the inverse of the differentiation. In differentiation, you multiply by j omega, but in integration, you divide by j omega. Then there's a constant associated with integration, and this constant is given by pi x naught, then d omega. The linearity property says that if you have a linear combination given by this representation in the time domain, then the Fourier transform of this representation in the time domain is simply equal to this, where x1 of omega is the Fourier transform of x1 of t, and x2 of omega is the Fourier transform of x2 of t. The convolution property of Fourier transform, it simply says that when we perform convolution in the time domain, it has the same effect of multiplying in the frequency domain. So when you convolve in the time domain, you do the Fourier transform of the individual signals, then you multiply in the Fourier domain or in the frequency domain. That's the property we have. That's the convolution property. The filtering property, you have the low pass filter and the high pass filter. The filtering property is that for the differentiator acts the Fourier transform of a differentiator is equal to j omega, and j omega effectively acts as a high pass filter, allowing high frequencies to pass through but attenuating the low frequencies, while this function acts as a low pass filter, allowing low frequencies to pass through while attenuating the high frequencies. And if we look at this particular Fourier transform, the one we had previously is the ideal case, but this particular, the Fourier transform of a to the minus a to u of t, is a low pass filter, or is a non-ideal case. It allows low frequencies to pass through while attenuating the high frequencies. I move to the modulation property. The modulation property is the dual of the convolution property. The convolution property says that when you convolve in the time domain, you're actually multiplying in the frequency of Fourier domain, while the modulation property says that when you multiply in the time domain, you're actually convolving. When you multiply in the time domain, you're actually convolving in the frequency domain, but with a factor of 1 divided by minus 2 pi. We go into an example. Find the transfer function for the system x of t equal to the y dt plus a yt. We are going to use the differentiation property. So the differentiation property says that the Fourier transform of this, of the differentiation of y of t, is equal to j omega multiplied by the Fourier transform of y of t. Then linearity property allows us to perform the Fourier transform of x of t to be x of omega t, and the Fourier transform of a y of t to be ay of omega, and allows us to add it together. When we collect the y omega times, we have this equation here, and separating the y omega from the x of omega, you get this. Then the transfer function is simply y omega divided by x omega, which is 1 divided by j omega plus a. The next question says that we should find the expression for y of t. So basically, we should solve this differential equation, and we are going to use Fourier transform to solve it. Then we know that the Fourier transform of a differential is simply multiply j omega, then the original the Fourier transform of y of t. Then the Fourier transform of this is simply 2 multiplied by y of omega, and the Fourier transform of this a to the minus t u of t. Remember that in the when we had this function in the last class, when we have e minus at minus at u of t, we got the Fourier transform as as this was the Fourier transform we got. So it turns out that this particular function is a standard function. Then this is a standard function. So if you have any signal of the form of this is the Fourier transform you have. In this question, this is the form we had it in. So it simply means that a is equal to 1 in the question. So in place of a, we're going to put 1. That's how we have it here. So the Fourier transform of this is given by this. And when we collect the y omega terms, we have this. Then making y omega the subject of formula, we get this. The question is to get the y of t. We don't have any function that can help us to convert, to do the inverse Fourier transform of this particular signal. So we first break it down into partial fraction. When we break it down into partial fraction, we get this. Then we know that this form is easier to work on because we know that the Fourier transform of a signal of this form is given by, so we know that the Fourier transform of a signal of this form is given by this. So here, this particular signal is kind of equal to this. So here, that means that a is equal to 2 here. So in place of a, you're going to put 2. Then in this case, a is equal to 1. So in place of a, we'll put 1. So that's just a to the minus t u of t. We do the third example. Find the Fourier transform of this signal. So this signal is just a repetition of what we did the last time. The reason I brought it is because we are going to do another the Fourier transform in the form of this. So in the first case, we had e to the minus at u of t. But in this case, we have e to the at u of minus t. Then we're going to go through the normal route to do it. So in place of x of t, we replace it with this. And u of minus t is a step function, but it has a value of 1 from minus infinity to 0. So we are removing this u of minus t, and we are performing the integration from minus infinity to 0 because u of minus t has a value of 1 from minus infinity to 0. That's why we remove the u of minus t, then we replace it with the limits of integration from minus infinity to 0. When we collect like terms, we get this, then the integration is given by this. Applying the limits, we are going to arrive at this function. So it simply says that for the first part, we know that if we have this function in this form, we know that, so if we have a function in this form, we know that this is the Fourier transform. It simply means that if you have a function of this form, we know that the Fourier transform is simply a minus j omega. That's what we are trying to prove. So a signal of this form has this Fourier transform, and a signal of this form, this is the Fourier transform. Now we use what we've gotten here in the highlighted equations to do our next example. And we are asked to derive the Fourier transform of this function. So this function can simply be broken down into this. So here you have an absolute value of t. So actually this function is actually the um, when t is positive. So this is the case of when t is positive, and this is the case of when t is negative, because here is the absolute value, and the absolute value is equal to the positive and the negative value. So in this here, this is when t is positive, and this is when t is negative. And the Fourier transform, just Fourier, try to do the Fourier transform of the right side and the left side. We already know the Fourier transform of this as this, and we know the Fourier transform of this signal as this. Then we just add it together and we arrive at this. So we know that the Fourier signal of a signal of this form is equal to, the Fourier transform is equal to this form as 2a divided by a squared plus omega squared. Now, this question stems from what we derived here. We're asked to get the signal corresponding to the Fourier transform of this form. And this particular what we got here, it's kind of similar to the question. So we're going to use, we're going to do the inverse Fourier transform, but using what we got here. So we know that a signal of this form has this Fourier transform. What we are going to do now is to represent our question in this form. Then from there, we'll work backwards. Then we'll try to get the original signal. That's the strategy we are going to use. So we're going to put our question in this form. So when we put our question, which is 1 divided by 25 plus omega squared, in this form, we're going to arrive at this. Now we have 5 squared plus omega squared. So we know that our a is 5, and we have the omega squared. Then we put a 2 here. Then our a has to be 5. So what you have here is simply, we are putting it in this form. But this is the original question. If you just leave it in this form, 2 times 5 is 10, but you have 1 here, you don't have 10 here. So that means that at this side, we have to divide both sides by 10, because this is our original question. Therefore, this, we have to divide both sides by 10. So you have 1 over 10. And instead of a here, you have 5 here. So instead of a here, you have your you have your 5. So root, this is actually root a squared. Root a squared. So it's simply a in this form. Yeah, you have a. So since our a is 5, so that means that the Fourier transform, the original signal that represents this Fourier transform, is given by this. And this is supposed to be a, not root a. It's supposed to be a. Derive the Fourier transform of a. It's supposed to be a. Okay. So this is the correct representation. So we know that we just put the signal in this particular form, because we know that the Fourier transform of this is equal to this. Then the last question here is to determine the Fourier transform of this signal here. We're going to use the duality property. So I mentioned that in the duality property, if x of t, if x of omega is the Fourier transform of x of t, then the Fourier transform of the Fourier transform of this, but now in the time domain, is equal to the original signal you have, but a factor of 2 pi, then at t is equal to minus omega. That's what the duality property says. So if you know the Fourier transform of this signal, it is possible to know the Fourier transform of another signal that is in this form, is exactly in this form. And the relationship between the Fourier transform is given by 2 pi multiplied by x minus omega. So in place of t here, you're putting minus omega, then a factor of 2 pi. Now we have this signal. So here should be A, sorry. Here should be A. So we have this signal here. And this signal looks familiar. It looks similar to this particular Fourier transform. So we're going to use the duality property. So we know that if you have a signal given by this, we know that this is the Fourier transform. Then, that being the case, if you have a signal of this form, then that means that using this formula, that means that the Fourier transform is given by the Fourier transform of this form is given by this. So this signal here is the same thing as this signal here. It's just that in place of the omega, you're replacing it with t. So in place of the omega, you're replacing it with t. So we know that if you have this signal, this is the Fourier transform. So using the duality property, it means that if you have this signal, so instead of omega now, you have t. We know that this is the Fourier transform. It's just 2 pi. We got the 2 pi here. Then in place of x at minus omega, in place of t, you have minus omega. So in place of t, in place of this t here, in place of this t, you have minus omega, and the modulus of minus omega is omega. So we still have this. Then remember, this is our question. Our question is 1 divided by 1 plus t squared. So dividing both sides by 2, you're going to arrive at this. And in this place, our a is 1. Our a is 1. So that means that the Fourier transform, so since our a is 1, so that means that the Fourier transform of this signal is given by this form. So in the next class, we'll talk about the discrete time, the Fourier series in the discrete time domain. Then we go into the Fourier transform in the discrete time domain.